What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 10, Section 7, Parametric Equation Graphs. Let's do it. Question 1, what are two methods used to graph parametric equations? So the first one is, of course, we could make a table with different t values and then plot out the points, the xy coordinates, and put them on a graph. And we could also use arrows to kind of indicate the progression, the direction of t going from 0, 1, 2, etc. And of course, the other way is to use a graphing calculator. Why are some graphs drawn with arrows? So the reason why is because it's showing the direction of the graph as t goes up. So, we might have a point here when t is 1. We might have a point here when t is 2. We might have a point here when t is 3. And we might then show it's going in that direction, right? So that's what the arrows indicate. Done. Why are parametric graphs important in understanding projectile motion? Because what we're really doing is we're modeling, actually, that's a great model for a projectile in terms of time, right? That's the third element that we're considering. So we're talking about time, and then according to that time, we're talking about horizontal, aka x trajectory, and vertical, aka y trajectory. So it's how does the horizontal distance and the vertical distance change as time progresses. All right, so for this one, we're going to fill out the table, plot the points, and then we're going to see what it looks like. So first, I'm going to plug in values -3, -2, -1, etc. in for t up here to get the x values. So -3 minus 1 is -4, -2 minus 1 is -3, -1 minus 1 is -2. So you can kind of see this pattern here, right? -1, 0, and 1. All right, now down here, we've got this value squared, t squared. -3 squared is 9. That squared is 4. -1 squared is 1, 0, 1, 4. Okay, there we go. Now let's plug and chug. So we see at -4, we've got a value of 9. -3, we have a y value of 4. -2, we have a y value of 1. And -1, we're 0 on that axis. And then 0, we pop back up to 1. And then back up to 4. So this certainly looks like a nice little parabola, right? And look at the direction. As t is increasing, we're going this way, coming around like this. So the arrows are going to go in this direction, right, as t increases. So that's how you do it. Done. So for this one, we're going to plug in these values for t. First, I'm going to start with x. So we got -3 times -2, which is 6. And then -2 plus 6 is 4. Here we got -2 plus 4, because -2 times -2 is 4. -2 plus 4 is 2. And then we plug in -1. -2 plus 2 is 0. So you can kind of see this progression. 4, 2, 0. And then plug in 0. You've got -2, right? We're going down by 2 every time. Plug in 1. -2 minus 2 is -4. For the y values, 3 plus -3 is 0. 3 plus -2 is 1. 3 plus -1 is 2, so you can kind of see the pattern. It's going to go up to 3 and then 4. All right, let's plot these out. So first I have 4, 0. Then I have 2, 1, right? Then I have x of 0, y of 2. So this is looking like a line. Then we got -2, and we got 3, and then -4, 4. So as we connect the dots, we've got this nice line like so. And again, we started out to the right going left. And again, we started out to the right going left. So we're going boom, arrows in that direction. So that's how you do it. Done. For this one, we're going to plug and chug into first x. So it's all of these values squared, right? All these t values squared. So I got -2 squared is 4, -1 squared is 1, 0, 1 is squared is 1, 2 squared is 4. All right, now it's t plus 3. So all of these plus 3. -2 plus 3 is 1. -1 plus 3 is 2. Then we got 3, 4, and 5. All right, now we got some good points. So first we have 4, 1. Then we have 1, 2. Then we have 0, 3, 1, 4, and 4, 5. So check this out. We got this nice little parabola. And since we started down here, we're going in this direction. The arrows are going this way, right? So that's how you do it. Done. So for this one, we're going to sketch the graph. And first, I'm going to make a little table with values from 0 through 5. And it pretty much chose those values because those are the t values they use in the back of the book. So we're going to do the same thing. Now we're going to plug and chug. So first, I'm going to get the x values. So first, the negative square root of 0 is 0. Negative square root of 1 is -1. Then we got negative rad 2, negative rad 3. Square root of 4 is 2, so that's negative 2, and then negative rad 5, all right? Now we've got the corresponding y values, and it's literally just equal to t, so 0, 1, 2, 3, 4, 5. Okay, let's plot these out. So first we have 0, 0 at the origin, then we have negative 1, 1, then we have negative rad 2, which is about 1.4, let's say like here, and that is 2. And then we got negative rad 3. That's about 1.7 or so negative. And then we're up here at 3. And then we got negative 2, which is at 4. And then we got negative rad 5, which is right around here going up to 5. So it looks like that. And so you can see it's kind of like this little curve thingy, like going up like that. And then of course, since we start here and we're going in this direction, the arrows are going to go this way as t increases. Done. So for this one, we're going to make another table, and I'm choosing values for t from negative 5 to 5, again, just because that's what they did in the back of the book. It's a little bit arbitrary, but this will give us a really nice picture of the graph. So first, we're going to get the x value. So we got negative 5 in here. That becomes 5 plus 2 is 7. Negative 4 becomes 4 plus 2, which is 6. So we can kind of see this pattern continue. 5, 4, 3, 2. Now when we get to 1, it's going to be negative 1 plus 2, which is 1, then negative 2 plus 2 is 0, and then negative 3, now we're dipping into the negatives, negative 1, negative 2, and negative 3. All right, what about the corresponding y's? So we got absolute value, very interesting. So absolute value of negative 5 is 5, 5 minus 5 is 0, and then we have 5 minus 4 is 1, 5 minus 3, because again, we're absolute valuing these. So it's not 5 minus negative 3, it's just 5 minus 3, 2, 5 minus 2, 3, 5 minus 1, 4, 5 minus 0, 5. And then 5 minus 1, again, absolute value of 1 is just 1. So now we're dropping back down to 4, 3, 2, 1, and 0. All right, let's plot these points. So first we have 7, comma 0 right here. Then we have 6, comma 1, 5, comma 2, 4, comma 3, 3, comma 4, 2, comma 5, and then we dip back down. 1, comma 4, and so on. So you can kind of see this pattern continue. So now as we connect the dots, we got it like this. It looks like an absolute value function. And again, since we started over here as t at the lowest value at negative 5, we know the arrows are going in this direction like so. That's how you do it. Done. So for this one, we got a little table here. I chose values for like pi halves, pi, radian values because we got trig functions, so it's going to make it easier. So first I plug in 0. Sine of 0 is, of course, 0. 2 times that is 0. Sine of pi halves is 1. 2 times that is 2. Sine of pi is 0, so that's 0 again. Sine of 3 pi halves is negative 1, so that's negative 2, and then we're back to 0. For cosine of 0 is 1 times 4 is 4. Cosine of pi halves is 0, so that's 0. Cosine of pi is negative 1, so that's negative 4. And cosine of 3 pi halves is 0. And then, of course, we come back to pi. Notice that 2 pi, and 0 are equivalent because they're essentially the same angles, right? They're coterminal. So now as we plug this in, we've got 0, 4. We've got 0, negative 4. And then we got negative 2, 0. And as you'll notice, we're kind of coming around in this direction. And what this is a nice ellipse. And so with the arrows, since we're going in this direction, we kind of have them come around like that way, clockwise, done. So for this one, we're doing it in degrees, not radians. But I chose degrees because, again, we have trig functions. So let's go ahead and plug and chug. Let's get the x first. So cosine of 0 is 1, squared is 1, times 3 is 3. Cosine of 90 is 0, so this one's 0. Cosine of 180 is negative 1, squared is 1, so that's 3 again. Cosine of 270 is 0, and then cosine of 360, we're back to 1. 1 squared times 3 is 3. All right, now we get our corresponding y values. Sine of 0 is 0 times negative 3 is 0. Sine of 90 is 1, squared is 1, times negative 3 is negative 3. 180, sine of that is 0. Sine of 270 is negative 1, squared is 1, times negative 3 is negative 3. And then we're back to 0. So we got some interesting points here. We got 3, 0. Then all of a sudden we have 0, negative 3. Then we go back to 3, 0. Then back to 0, negative 3. So notice this little bouncing back and forth. So we got a line that's going in both directions, it seems like, and the way they've notated this in the back of the book is kind of like arrows coming this way and arrows going that way. So it's bouncing back and forth, back and forth. So that's how you do it. Done. So for this one, I've made a little t table, and we're going to plug and chug in for t. And I just got values from 0 to 180, and that's going to give us plenty to work with. So first, remember, secant is really 1 over cosine of t. So cosine of 0 is 1. 1 over 1 is 1. Cosine of 30 is rad 3 over 2. So the reciprocal of that is 2 over rad 3. And that's about 1.15. Secant of 60 is 2. Secant of 90 is undefined. And it's sort of like as we get closer and closer to 90, it's going to get bigger and bigger and bigger. So that's just something to keep in mind. Now we say secant of 120. That's the same reference angle here, but it's negative because we're talking quadrant 2. So that's negative 2. 150 is going to be the same as 30, but negative, of course. And then this is going to be the same as 0, but negative as well. Now we get to tangent squared of t. So tangent of 0 is 0. 0 squared is 0. Tangent of 30 squared is 1/3. Tangent of 60 squared is 3. And then we got the same values here. And again, because it's squared, everything will continue to be positive. By the way, tangent of 90, that's going to be undefined. But then we got 3, 1/3, and 0. So then plotting these out, we got 1, 0. We got 1.15, 1/3, which is like maybe up here. It's hard to approximate, right? Because that's 2. So we got to be careful. And then we got 2, 3. 3 is like here. And if we continue this out, we'd see it would kind of get bigger and bigger and bigger. So it's kind of shooting off like this. But there's kind of a starting point here. And then over here on the negative side, we're starting with, let's start over here on this side, -1, 0, then -1. So you see it's going almost like a mirror, right? And then -1.15, 1/3, and then we got that -2, 3. So it's kind of coming back up. But if you notice, even though I drew it right to left, it was really going left to right. We're starting out here and coming down. So the arrows are going to be in this direction, and then over here the arrows were in this direction, the direction that we kind of plotted these points out. So that's how you do it. Done. So for this one, I'm actually going to turn it into a Cartesian equation first because I just feel like it's going to be easier, and then I'll graph it, and then I'll show the orientation and everything. So again, we want to do a little substitution, right? If I take the first equation, I add 1 to both sides, I get t equals x plus 1. Then I can substitute this in here for t and get our Cartesian equation, y equals negative, and in place of t, I'm going to put x plus 1 squared. And this is your typical equation for a parabola, right? It's a vertex at -1, 0, so -1, 0, and it's facing down because of that minus in front. So we got a couple points like this, and it's a parabola coming down, and like so. Now the question is, which way do the arrows go? So we can kind of think like when t equals, let's say, -2, it's really the x value is at -3. We're at this point. When t equals -1, then we come to this point, then 0, then 1, then 2. So the order it's going in is in this direction. So that's how you put in the arrows. That's how you do it. Done. So for this one, I decided to make a little table, and then we're going to plug and chug. And I chose values that are going to be nice for this trig function and that trig function. So cosine of 0 is 1 times 2 is 2. Cosine of pi halves is 0. Cosine of pi is -1 times 2 is -2. And then we're back to 0. Sine of 0 is 0. Sine of pi halves is 1 times -1 is -1. Sine of pi is 0. And then sine of 3 pi halves is again negative, or is -1 times negative is +1. So we got these interesting points. We got 2, 0. We've got 0, -1. So we're going in this direction. Then we got -2, 0, and then 0, 1. So you can see we got a nice ellipse here coming around like so, with arrows going in this direction clockwise. Now to turn this into Cartesian equation. So basically we got x equals 2 cosine t, y equals -sine of t. I'm going to square both of these. So this one is going to be x squared equals 4 cosine squared t. This one's going to be y squared equals sine squared t, right? When we square both of those. And this one I'm going to divide by 4 because now I got something special. Now I got something that equals cosine squared, something that equals sine squared. And the reason why that's cool is when I add sine squared plus cosine squared, I get 1, which means if I add x squared over 4 plus y squared together, it equals 1. And there's my equation without a t. Boom, done. So for this one, we got a few different values of t here, and then we got to plug and chug for x and y. And we're going to maybe use a calculator just to approximate a little bit because you're going to get a little crazy. So I plug in 0, I get e to the 0, which is 1. And this is also going to be e to the 0, but a negative in front, that's going to be -1. Then I plug in 1, I got e to the second, and e squared is about 7.4. This one will be e to the 1 negated, which is about negative, let's just say approximately negative 2.7. Then we got 2. Plugging that in, e to the 4th is about 55. And then down here we have e squared negated, which is negative 7.4. Then we got the 3, so that's going to be e to the 6th, which is about 403. And then here we have negative e cubed, which is about negative 20. So we got some decent points here, so let's plug and chug. We got 1, negative 1, maybe like here. Then we got 7.4, negative 2.7, maybe here. We got a big jump to 55, negative 7.4, maybe like here. These are just approximate. And then we got 400. Whoops, doesn't really fit, but let's say 400 is right around here and then down to negative 20. But that gives us enough to connect the dots. So you can see it's kind of going like in this direction. So the arrows would be going this way, and that's how you do it. Now let's turn it back into Cartesian equations. So to isolate t, I'm going to take natural log of both sides. We're going to do the x1. So I'm going to say ln of x equals ln of e to the 2t. Using my logarithm rules, I'm allowed to bring this down as a coefficient. So now I have ln of x equals 2t ln of e. Ln of e, by the way, is 1. And then divide by 2, t equals ln of x divided by 2, and then I can take this and replace the t up here. So it's y equals negative e to the ln of x divided by 2. Now I could simplify this because that dividing by 2, I can also think about that as multiplying this thing by 1/2. And when I multiply by 1/2, my rule for logarithms allows me to make that as an exponent. So it's really ln of x to the 1/2 power. And then there's another rule. E to the ln of something is just that something, right? These essentially cancel out. So we're left with y equals negative x to the 1/2, which is the same as negative square root of x. So that's the final function, done. So for this one, we're going to plug and chug, starting with negative 5 for the x equation, and we're going to create some xy coordinates. So we got negative 5 times 2 is negative 10, right? So everything is doubled. So this is negative 8, negative 6, negative 4, and so on. Now we get to y equals t squared, so it's all these values squared. So negative 5 squared is 25, then we got 4 squared is 16, 9, 4, 1, 0, and then on the other side, same thing. So it looks like we got a nice little parabola starting at negative 10, 25, negative 8 is 16, negative 6 is 9, negative 4 is 4, negative 2 here is 1, and then we got that nice 0, 0, and we're going to see the same pattern kind of mirrored on the other side. And then as we connect the dots, we get this nice little parabola. Again, that's what they wanted, right? From negative 5 to 5. And the direction is going this way, just how we plotted it, right? We went from increasing values of t, so it's going to go in that direction. Boom, done. So for this one, we're going to again make a table, and I've just plugged in some nice values here. Now, the reason why I've chosen these values for t is because they're all perfect squares, and that's going to be convenient because then I don't have to use a calculator to calculate my corresponding y values because of that square root. So let's first do the x's. So x's are all whatever t is, but negated. So 0 would be 0. Then we got negative 1, negative 16, negative 100, and negative 400. For my corresponding values of y, I'm taking the square root of these t values. So square root of 0 is 0, square root of 1 is 1, then square root of 16 is 4, square root of 100 is 10, and square root of 400 is 20. So look at these beautiful coordinates. I got 0, 0, then I got negative 1, 1, that's like really hard to draw, but like something like this, I don't know. And then we got negative 16, 4. So let's say this is 20, maybe here's negative 16, and 4 is right up here. Then we got negative 100, and that's shooting up to 10, and then we got negative 400, and that shoots up to 20. So we got some nice points. I think this one's like not correctly positioned. Maybe it should be there, and then we can kind of draw it out. And we were obviously starting here at t equals 0 and then going left, so the arrows are going in this direction. So that's how you do it. Done. All right, so for this one, we got t values from negative pi halves to pi halves, and I added in a 0 and negative pi thirds and positive pi thirds, so let's plug and chug. So first of all, we have to remember that secant is 1 over cosine. So starting at negative pi halves, right, cosine of negative pi halves is actually 0, so this is going to be undefined. So first, we got negative secant of negative pi thirds. So secant of a negative angle, like negative pi thirds, that's going to be in the fourth quadrant, actually, but cosine's still positive there. So that's going to give us 2 negated is negative 2. And we're going to get the same thing for positive pi thirds. It's still going to give us a -2 there. For pi halves, we got an undefined situation here as well, right? Because that's going to be undefined just like here. We're getting a 1 divided by 0. And then cosine of 0 is 1, 1 over 1 is 1, negated is -1. Cool. What about tangent? So tangent of negative pi thirds, that's going to be a negative rad 3. Tangent is 0, 0. Tangent of pi thirds is positive rad 3. So we're going to see if this kind of gives us enough of a picture. So what we've got is -2, negative rad 3. So -2, negative rad 3, somewhere around here. Then we got -1, 0. And then we got -2, positive rad 3. So we're seeing something like this. Now, if we continued out the trend, maybe chose something in between negative pi thirds and pi halves, what you're going to see is this line kind of continuing down like so. And as we come up, right, so, and by the way, we're going in this direction, starting and negative and kind of coming up to -1, and then it seems to turn a corner and then shoot back up, right? So what is the direction of the arrows? It's going in this direction, kind of coming up and around. So that's how you do it. Done. So for this one, we're going to use a graphing calculator, and we're setting A to 3 and B to 2 on this domain. So let's check it out now. So for this one, the way I graphed it is, again, when we're trying to graph parametric equations, I put this in as the x-coordinate in the coordinate pair, this in as the y-coordinate, and then I set B and A to what they said, right, 3 and 2. And that's the graph. That's what it looks like. And the only other thing to note on the graph is the direction, and the direction is going this way. So it's kind of climbing up in this direction, like so. Boom, done. So for 37, we're graphing from the domain negative pi to 0 with A equals 5 and B equals 4 with this equation. So let's do that in Desmos now. So here we've got the function plugged in just like they showed us in the book, and I've substituted 4 for B, 5 for A with that domain from negative pi to 0, and here's the graph. And just so we can see the directions, the arrow is going up again, right? It's winding around like so, and that's how you do it. Done. So for this one, if you kind of saw the trend as A and B sort of increased, what you can say is this is essentially going to be a curvy graph like 35 and 37, but almost like 100 oscillations. So we're going to show that now in Desmos. So here I've put in the two parametric equations into coordinates like so. I set A and B as they specified, and this is kind of what it looks like. So you can see if you really zoom in, it's going back, forth all those times. So it almost looks like a full square when you really zoom out. But anyways, that's how you do it. Done. If the parametric equations x equals t squared and y equals 6 minus 3t have a graph of a horizontal parabola opening to the right, which means it would look like this, what would change the direction of the curve? Meaning, how would we make it open to the right? So clearly what we're modifying is not the y values, right? We could leave the y values the same. We need to modify the x values. So let's say, if here x would be like 3, I'm just making this up, and down here would be 3. We need that to be negative, right? We need to flip it, meaning all we got to do is take our x function and negate it like so. And that's how you do it. Done. So here we're meant to describe the shape, and if we can see that x is linear, meaning it would be something like x of t equals t, that would be linear. And then y is quadratic like so. This is a parabola, and it's going to be an upwards facing parabola. So that's how you do it. So for this one, the typical way that we write a circle is where x simply equals cosine of t and y equals sine of t. So this is our typical starting point for a parametric equation circle. And the radius is whatever goes in front here and here, right? We'd have a horizontal and a vertical radius. We want them both to be the same if it's a circle, right? If it's an ellipse, maybe we have a different major and minor axis. So both of these are going to have a radius of 5 like so. And that's how you do it. Done. So for this one, we're meant to graph using a graphing utility, and I'm going to do that now in Desmos. So now we got A equals 1, B equals 2 with that correct domain put in there, and we got this really interesting shape, looks like an infinity symbol. And the direction we're going in, starting when t is 0, so it would be sine of 0 and sine of 0, 0, 0, is going up. So we're kind of going in this direction all the way around in this figure 8. So that's how you do it. Done. So for this one, we're going to graph these equations in Desmos with the following values of A and B. So let's do that now. So here we kind of see that we have almost this line. And so originally it's going to kind of go up, 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 up. And then as we start to get closer to the third quadrant, we're shooting back down. And then boom, third and fourth quadrant are going to be sort of down here. And then it's going to shoot back up. So it's going to go back and forth. So we can sort of say going up, then down, multi-direction. So that's how you do it. Done. So for this one, we're going to plot these two parametric equations with the following values of A and B. So let's do that now in Desmos. So now we got this super cool shape, right? And again, starting at the origin, we're going up. So that's the direction. So when we put those arrows in, we're kind of going up and around like so. And you see it kind of just like keeps going whoop in this like interesting pattern. But that's the general idea. That's how you do it. So for this one, we have x equaling this function, y equaling this function, and we're trying to figure out the values of A, B, C, and D to get this graph. So we're going to look at Desmos and we're going to kind of play around with the values. But the first thing I want you to notice is that the domain is essentially from -4 to 4. That influences something very important. That influences this A value for the x function. So starting everything just at 1, 1, 1, 1, I know that A needs to be 4, and you see now it's expanded out correctly. Likewise, I see it's going from -6 to +6, which means that C value kind of is going to correspond to that height. So we're going to change that to 6. So here we go, and there's 6. So now we got an ellipse. Now we're seeing that there's sort of like these vertical loops, and how many oscillations are we seeing? 1, 2, 3. So since we're going left to right, I'm going to say that we change that B value to a 3, and boom, we got it. There's our interesting kind of hourglass looking figure. That's how you do it. Done. So for this one, we're meant to find the values of A, B, C, and D for these two functions such that we kind of get this cool shape here. So we're going to start to figure out these constants. Now the important thing is I see to start with, from left to right, we're going a distance of 4. So that's going to impact the A value. And up and down, we're going up and down by 3. So that's going to impact C. So I'm going to set A to 4 and C to 3. So sort of going from left to right, it's sort of like going up and then down. So I'm linking that to a value of 2 for going left and right, aka for B. And now that's going to turn this almost into some sort of a parabola going left. And then when we're talking about vertical, it's like we're going up, down, up. So I'm going to link that with the value of 3 for D. And as we change that to 3, now we get the shape in question. So that is how you do it. Done. So for this one, we're meant to graph all 3 systems of parametric equations on Desmos on this domain. So let's do that now. All right, so here are the 3 graphs. So this is the first set in part A, and you can kind of see there's the graph as we turn that off. We get the next one, cosine t plus t sine t minus 1, like so. And last but not least, the third one, and that's how you do it. Done. So for number 59, we're meant to graph these sets of parametric equations from this domain. So let's do that now. So now looking at the 3 graphs, here is the first one, -4 pi to 6 pi. Here is the second one, like so. And finally, here is the third one. And that's what it looks like in Desmos. Done. Explain the effect on the graph of the parametric equation when we switch sine of t and cosine of t. So what I'm guessing they're referring to is swapping cosine to sine. I'm not exactly sure what they mean, if they mean with these functions in particular. What they talk about in the back of the book is that the y-intercept changes. I do believe that's something that does change. And we can quickly compare the B and the C, for example. So that's these two. And we can see that, I mean, that is one of the things that changes. So if that is the correct interpretation of this question, that's how you do it. Done. An object is thrown in the air with a vertical velocity of 20 and a horizontal velocity of 15. If the object's height can be described by the equation blah, 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 while the object moves horizontally with constant velocity of 15. Write parametric equations for the object's position. Okay, so when we're talking about a constant velocity, that means the horizontal position is constantly changing 15 feet every second. So it's 15t, right? And then y of t, they already gave us. Now that we got our parametric equations, we can find the xy equation by isolating for t and then plugging and chugging. So here I'm going to divide by 15. T equals x over 15. So then now we get our equation of y by replacing every instance of t with x over 15. So I got y equals -16 times x over 15 squared, right? Just plugging in for that, plus 20 times x over 15. That's how you do it. Done. For the following exercises, use this scenario. A dart is thrown upwards with an initial velocity of 64 feet per second and an angle of elevation of 52 degrees. Consider the position of the dart at any time. Now, when we're looking at projectile motion, okay, x of t is going to equal the initial velocity times cosine of the initial angle of elevation times t. And the height, of course, is going to be negative 16 t squared plus initial velocity times sine of theta times t plus the initial height. Now, of course, the initial height is 0 because we're starting at 0. And then now we can plug and chug. So x of t equals initial velocity 64 times cosine of 52 degrees, and then times t. And then for y of t, we've got, again, negative 16 t squared plus that initial velocity of 64 times sine of 52 times t. That's how you do it. Done. So to answer 67, when will the dart hit the ground, we need to know our answer from 65. So these are the two equations that are modeling this situation up here. So when will it hit the ground? We want to know when is the y, or the height, going to be equal to 0. So we're going to say 0 equals that equation. I want to get an approximation for 64 times sine of 52. So I'm going to just see what that is in Desmos. Then I'm going to subtract this quantity from both sides. Then I'm going to factor negative 16t out from this equation. And then we got t minus, and then 16 times 4 is 64. And that's that. So now we can get our two values. So of course, when we plug in 0 for t, that's going to zero this out. But that's, obviously when it's starting. We want to know the later point when it's going to hit 0 again. And that's going to be when this equals 0, right? Because we got it in factored form. So it's t minus 4 sine of 52 equaling 0. So add 4 times sine of 52 to both sides. And there's our answer. And to get an approximation, I'm going to plug it into Desmos. And we get approximately 3.2. So we say 3.2 seconds. Boom, done. For number 69, at what time will the dart reach maximum height? And again, to do this, we need the equations that we found in question 65. So at what time will the dart reach maximum height? So maximum height has to do with this function. When is it going to be at its max? Well, this is a quadratic, so it's going to have a vertex, right? It's going to kind of look like this. So when, or at what t value is it going to be at that maximum point? That's the vertex. That's what we're talking about. So we can get the vertex by taking b, or negative b, I should say. So negative b, 64 sine of 52 over 2a, 2 times negative 16, which is negative 32. So let's see what that is in Desmos. This is our t value. And rounded to the nearest tenth would be 1.6. So we'll say 1.6 seconds is when it reaches that max height. Done. So for this one, we want to graph these parametric equations, and it's a hypocycloid. So let's do that in Desmos now. So again, we put in the parametric equations, the x1 in the x position of the coordinate, the y1 in the y position, and look at this really cool shape. That's how you do it. Done. So for this one, we're meant to graph it in Desmos. I'm going to plug it in now on this domain. So again, we put the x function in the x position of the coordinate, the y function in the y position of the coordinate, and check this out. Check out this cool shape. That's how you do it. Done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.